Welcome everyone. Today we'll be discussing part 2 of directive-based programming with OpenACC. My name is Daniel Howard. I'm part of the consulting services group at CISL and in NCAR. Today we'll be continuing on with mini weather from Matt Norman's little mini app for weather-like simulations. We'll be using OpenACC again to develop for GPUs, extending from that part 1 material. So hopefully you have had a chance to review that. But today we'll be focusing on a few different aspects of OpenACC. We'll be focusing on data constructs. We'll touch on routine directives and other clauses, as well as some more advanced concepts if we have time later on the session. Otherwise, those will be left as review materials for yourself afterwards and following the session as on your own independent study and time. So again, be sure to start up a Jupyter session on Casper. You can use, we recommend actually using the batch nodes during this workshop time, just to make sure that you have adequate compute time during the session. You should only need one CPU and no GPUs for running the notebook, and we'll submit GPU jobs from within the notebook. For workshop etiquette, please make sure to mute yourself and turn off video during the sessions, and feel free to ask questions in chat and or raise your hand and unmute will be used during the Q&A at the end. And if you have a pressing question, feel free to raise your hand during the discussion, and we may have time to address that during our presentation. So again, notebook setup. If you have the notebook open, you should see some of these description slides open. So basically, I can switch over here briefly and show you what you may want to change here quickly is change this to GPU workshop and GP100. This just helps make sure that we have we only have a limited number of V100s, so we want to make sure that you have our accessing a reservation set up for you during the workshop. So go ahead and run that cell with Shift Enter, and then you can go ahead and test that the current build of MiniWeather works. You can run this CMake file, shell script to set up our environment. And then after that setup, you can then run this make command. You likely will need to do this to set it up for the example exercise we'll be running. And then you can submit the job, making sure that you're running the OpenACC test exercise 2 executable here to be sure that it's set up correctly. If you have errors in the output, be sure to let us know. There may be an extra async clause from testing earlier that may need to update. Otherwise, let's go back to the slides. Basically, what we're going to be focusing on today is data locality and data movement. So previously, our work was utilizing the GPU managed flag in order to set up a unified memory environment. This basically allowed us as programmers to not have to worry about memory movement within the OpenACC runtime. So if you recall the design of heterogeneous GPU accelerated systems, there are different spaces for the CPU and the GPU devices when you're programming for GPU acceleration. So, essentially we have this little model here. We have a CPU on the left, GPU on the right. CPU has this much larger capacity memory that typically you might recall as DDR memory. GPU memory has this high bandwidth memory, HBM2 memory, and they're all connected in these various ways. So there's these different arrows between these different spaces. And the size of these arrows is important. Basically, when we want to move memory from the CPU to GPU, we have to use the I/O bus or PCIe bus, and that is unbearably slow compared to these other connections we have between the CPU and its memory and the GPU and its memory. So for example, the PCIe bus is about 16 gigabytes per second, whereas the high bandwidth memory is about 900 gigabytes per second for V100s and even faster for A100s. So to moderate that movement of data between the CPU and GPU, OpenACC has these data directives that we can use that allow us to manually define how we want to be moving data between the CPU and GPU. This often tends to perform better than using just the GPU managed flag, though if you do happen to have a well-designed code that is cognizant of how that data is moved between the CPU and the GPU managed can do just fine, but you typically want to be designing your program to have in mind throughout the execution where data is and where it's located and where it should be going. So these clauses are the types of examples you can add on to different compute constructs or even in its own data directive regions themselves. So Each clause can reference, a list of variables. You can even then reference either the full variable itself, and so long as the compiler knows the size of the variable, you don't need to specify the size. But you can also then specify even slices of like an array if you want to pass only a subset of that variable to the GPU, or back from the GPU to the CPU and vice versa. So the scope of these directives, they basically have to be aligned with either a structured data region or an unstructured data region. So structured data regions are basically localized regions of code, and they essentially are also paired with automatically any of the previously worked on ACC kernels or parallel serial construct regions we use, or we also have this new direct construct region, an ACC data region that you can use. There's additionally an implicit data regions you can set using ACC declare, and that will take on the scope of the function or subroutine of program that it was called within. These will use structured reference counters, which we'll talk about a little bit later, while the unstructured data regions, these basically use these ACC enter data and ACC exit data that don't necessarily have to be matched up with each other. They can be in an unstructured way across your program. These will use a different reference counter called dynamic reference counters. So particularly, you might be more interested in unstructured data regions if you're using an object-oriented code. We might have multiple different source files and regions of the runtime you have to be navigating across. It might be difficult to set up structured regions effectively from a programming standpoint. Other specific clauses that might be useful within these contexts basically are limited to certain kinds that are allowed on each particular type. So unstructured data regions can only use certain clauses, and structured data regions can use other clauses, and there's also other limitations. So for example, that present clause, which defines when data is actually a variable on the GPU, that can only be that cannot be used on the enter and exit data regions, since there's not a defined region on which to define when the data is present. But it can be used on the structured data regions. The delete clause can only be used on the exit data region, as it's unclear, say in a structured data region, if you want to delete it at the entry or at the exit of the region. If you want to see more details about those specific rules and limitations, feel free to reference the quick reference guide linked here in this on this page. We will not cover a few of these pointers, but you're again welcome to refer to the reference guides and specification for more details on those types of clauses. So we'll go forward and just kind of like help visualize what basically these data directives are doing. In the code example here, basically, every parallel construct we might have, such as ACC parallel, there's always an implicit data region with that. So when you call ACC parallel, it does first create a data region, and then it creates a parallel region. And you can see kind of how they're commented within that code block, where those kind of regions lay out. You can specify maybe a larger data region by using those data clauses previously. And we'll talk about that in a bit further. But nonetheless, in the following images, we'll have this sort of setup here, where we have the data region, which is in this kind of beige color, and the parallel regions in this more bluer color. And we'll be referencing the CPU memory by the black line and the GPU memory by the green line, that they'll be encapsulated within any of those regions or within the larger data region. Appreciation goes to Idris France for inspiration for their for this type of imaging framework for showing this concept. So basically, OpenACC program without data management. This is what we did prior to today. We had basically all the different parallel regions, the implicit data regions that are with them. And if you looked at the minfo Excel output, you would see that the compiler was automatically generating for you all these various copy in, copy out, copy directives that manage how data was moving onto the GPU during execution and off the GPU after execution. So you'd see for a copy in, it only copy in data, copy out, it only copy out data, etc. Create, it would just allocate data. That's an important one if you want to avoid data movement entirely. But nonetheless, you can see for every single kernel that's encountered, it has to do that data movement every single time. That can get very expensive very fast and cause very many unnecessary transfers. If we added a structured data region, say across the sequence of parallel kernels we might be running, we would then reduce our data movement to only the beginning and the end of that data region where that data is brought onto the GPU. So this drastically reduces the amount of data movement required, and thus then utilization of that slow memory speed PCIe bus that goes between the CPU and the GPU. There might be other concerns if you need to update between kernels, the data that's on the GPU, but that'll be discussed a little bit later. So if we want to go to, here's the exercise portion to like implement some of this. We basically want to go to the exercise 2 file we have within the Jupyter Hub environment you have set up currently. And you want to go to line 128 and set up, basically we have this to-do section here for managing GPU data. We're going to be setting up these data regions around basically our main time loop here. So this is just an example here, but for the code, source code itself, all we're worried about is setting up a data region and the appropriate variables we want to be passing into that data region during the execution of the main time loop of the program. So let's go over to our document here. Basically, we have here's an exercise here. You can click this link here to open up the source file. Let's go up to line 128 it was, or if you like, you can search to do manage GPU data. And I already have provided hints for you in terms of like the types of variables we need to be concerned about. Since this is a larger source file, larger program, it might take a while to do that analysis, but nonetheless, you basically have to go through this main time loop here, if you did not have these hints, and check what data is being used within each of these sections. So for example, we're calling perform time step here. We're passing in the state temp, flux, t-end variables, and this DT variable is a scalar, so we don't actually have to worry about scalar variables. We usually only have to worry about array variables such as these ones. But there are also further variables called within this time step loop. So if we go to this these GPU data hints, which is just a little bit above here, we're defining basically all these different variables that are being used within this main time loop. So let's start with this first set of variables here. We have the hydrostatic density, hydrostatic theta, temperature, and then all these different other variables are important in terms of these computations being done. So essentially, for these cases, all of these are initialized on the CPU if you did this analysis throughout the program, and then used on the GPU. These variables are then never modified after being initialized, and thus describe static properties of the domain. So given that, does anyone have an idea about which clause we would be using in terms of copying in, copying out, or copying the data onto the GPU here that'd be most effective for the compute region we need encapsulated down here? So let's add the ACC data clause, and then from here we want to then add we're going to first close the data region, end data. But basically, we need to define here which clauses we need to use on that list of variables there for this particular section of code. So if we go back here, we basically only need to worry about copy in, copy out, or create. Which one for the static variables do we need to, static variables, hydrostatic density, hydrostatic vote times T, density, etc. Which of these, which data clause do we need to use? Feel free to raise your hand or comment in the chat what you think is the correct answer. Well, in this case, yeah, copy would work. Copy would definitely work. Is that the most optimal choice here? So if you put copy here and all those variables, basically we're copying in all of them throughout this data region, and then at the end we're copying it out. However, if you recall, all of these are initialized on host and then used on GPU, but then they're never modified after being initialized and described as static properties of the domain. Because they're static, we really only need to copy them in once. And that basically is then sufficient for our needs on managing this data domain here. And actually, I'm realizing as I'm putting this in here, this needs to go a few lines up to encapsulate these additional clauses the reductions and outputs clauses, because these also are using some GPU variables. So we also need to modify, check these other GPU data objects that be also on the GPU. So the next ones we need to look at are the state and state temp variables. These are used in parallelizable regions, like above, the previous ones we just did. And then both are initialized on the CPU as before. So then they need to be copied into the GPU after being initialized. But then only the state variable is needed for IO output. The state temp variable is not needed for output or passing back to the CPU at any time for execution. So in this case, the state temp variable would be needed as part of that copy in list. But Matt was correct before in terms of now the state variable is needed as a copy in because it needs to also be copied out at the end in order to process output appropriately. The last set of variables we have are these flux, t-end, just fluid state tendencies, as well as buffers for the MPI exchanges when we eventually work on multi-GPU implementations of this model. So in this case, these variables are again used in parallelizable regions that are within that time loop, but they're only computed or instantiated inside those regions. So then of those four options, copy, copy in, copy out, and create, which one would be used here for these variables? In this case, we would actually be using the create clause because they're not being initialized on the CPU and they're only being worked upon once you actually get inside the GPU regions. This basically, the create clause essentially then avoids any data copying entirely. So that's just one additional way to optimize data movement, and thus, in a sense, then reducing the amount of data transfers ever required. So after we have those set up, you can save it with Command or Control S. Should save. Let's see. And then we can see if it's not wanting to save for some reason, save file. There it is. Okay. And then we can basically build the new file here and then run our new test on the GPU 100 we had set up previously with the notebook setup cell. So here we'll be running that same GPU workshop project and then our GPU workshop queue, and we're also setting on the GPU type. So nonetheless, after this goes through and rebuilds the model, you'll see it's going through. It's taking a little bit of time. It appears maybe the node amount might be a little slow currently, but nonetheless, hopefully you're going a little bit faster. But you can see then the output, and actually from what I expect here, the output from the model after it runs, it'll take a little bit now, will be a little, will actually be incorrect now because there's some additional steps we need to do after we've done that work. So some questions to think about, which I'll leave you to answer to yourself at your own time after the session. Basically, we already deciphered some of that live. Which clauses do you need to use to ensure the data is available on the GPU? That is just a copy clause. Copy clause is for sure, go-to clause to make sure everything works. But if you want to be more optimal, you need to then choose between whether you need the copy in or the copy out or the create clause. So while that's doing its work in the background, I'll continue on to the next slides. But any questions in the meantime? Yes, I see that the font might be a little bit slow when I'm in the live coding sections, and next time when I'm back there, I'll try to increase the font size. If you have any questions, feel free to add them in the chat. Otherwise, I'll keep on going. So one of the issues that we need to correct if you run that particular example is basically we have to then use the update clause to make sure that the data that's on the CPU and the GPU are in sync. But whenever we're outside a GPU compute kernel, where you might be calling a CPU process that's then using data that's expected to have updated values that are now only on the GPU, but then no longer on the CPU. So this is done with this update directive here there are basically two kind of like options of it. There's update host, or there's you can use the same alias update self for basically copying listed data variables back to the GPU device, back to the CPU from the GPU, as well as then there's update device, which is basically copying variables from the CPU to the GPU. That there's, to note, you cannot use this update clause directive within a compute construct. That has to be outside of compute construct, but still could be within a data region. The present clause is also important in some of these cases, just to help also like not only readability of the code, just to let you know when data variables are present within a particular compute kernel, but it's also just gives you an idea of when data is actually present within a particular kernel, and helps give that hint to the compiler to let it know it does not need to move data. But when you are using that present clause, it doesn't necessarily guarantee that data is still in sync with the data on the CPU or the GPU. So you still might need to be using the update directive in order to ensure that synchronicity between the data on each of the separate memory spaces. So as an example, in terms of just some explicit variables, if we go back and forth copying or creating or copying out all these various objects, say we start with an initialized set of A, B, C, D, they're all 0. We initialize them to some values on the CPU. We can then call copy in, create, copy out D. You can see what happens when we enter this data region here and copy in these variables. So we see that A and C are copied in, B is created and allocated. So there's just empty, it's a null values is just there. There's also an option to add a 0 argument within the create clause in order to initialize it to 0, but we're not doing that here. There's a copy out clause. So essentially we've also then initialized the D variable with the copy out entry in the data region, but it's only going to be copied out at the end here when we exit it. So at the end, we did some GPU work in this purple section here, bluish purple section, and D becomes 158. Later on, D is then copied out here. That update directive we just discussed, say we now did that work on the B variable here, on the CPU was -4, and then now on the GPU becomes 26. But if we want to do some work here on the CPU that's relevant to the B variable, we'll need to use an update self clause when we're still within the data region to do that. And you notice even if we weren't within that data region, B is going to still stay on the GPU the whole time, because we only use a create clause. And so if we just exited the data region without doing anything with B, such as this update self directive, B would have just disappeared and never really would have been of a concern on the CPU side, except for what the CPU initialized it here outside of the data region and then the parallel region here. So hopefully this gives a brief example in terms of like how that data movement happens within certain variables. But the one important point to make here is some of these reference counters that also are aligned with any of these variables we set on the CPU or GPU. So in data clauses, basically, there's also this hidden reference counter or attachment counter for device pointers that are also initialized whenever you create data on the GPU. There are separate counters distinct from each other for both structured and unstructured data regions. Basically, these counters track the movement of data between the CPU and GPU, and only then process that movement whenever there's an increment from 0 to 1 or decrement from 1 to 0, essentially signifying that data should no longer be present on the GPU, or data as now should be present on the GPU. So in the case of using the copy clause, say we want to copy A and B from CPU to GPU, when we initially enter that region, the reference counter will increment from 0 to 1. But say within that region, there's another kernel that calls copy. That reference counter would now increase from 1 to 2. But since it's not going from the 0 to 1 increment, no copy action is actually being performed. When that kernel exits, that reference counter now decrements to 2 to 1, still no copy actions performed. But then once we reach the exit of the data region, that is when the decrement performs, because now through that whole process, that tracking of that counter will now decrement from 1 to 0, and thus then indicate that copy out should then be performed. So this is just an important concept just to have you back in your mind in terms of like how the OpenACC runtime is tracking the appropriate times and needs for moving data whenever it's necessary. So that is maybe then an important reason to consider the use of ACC update, since at some points you might be thinking by just adding the copy clause, it'll be moving data. But if you want to guarantee it's moving data, you want to be then using the ACC update clause. So the last point or option there is also the finalize clause. We don't have any examples I'll cover there in terms of utilizing that particular indicator in OpenACC, but nonetheless, that is valid really only for the OpenACC exit data directives on the delete, detach, or copy out directives. So that essentially forces the reference count to 0 and thus then makes that copy out action occur, or whatever action you're asking it to do. So again, referencing these counters, back again with that now larger data encapsulated region. Say we have an A variable that's either being applied in a copy in, a copy out, create, etc., any of those directives. When we enter the data region, we now make this A_D, that's device variable is now there. And now when we move in, that A reference count is increased to 1. But any of these regions we enter and exit, basically that reference counter goes up and down each time. But the only time it's then actually an action is performed is when it gets returned to 0 at the end. So you see these red boxes here indicating that movement from 0 to 1 means that one of these actions is being performed, either copy in, copy out means nothing's happening here, we'll wait till the end, but copy here or create is actually happening. But nonetheless, those reference counters are always there in the background, keeping track of when these actions should be performed. So in addition, if we did need to work on data on the CPU side between any of these kernels, you then want to use these update host or update device directives. And those could be, say, within this region here, which is on the CPU processing part of the application. These bluish regions are processed on the GPU, where the beige regions are on the CPU. And if we wanted to then be using, say, the A variable after may have been modified within this region back in the CPU, we want to then use the update host. So then it would move data from the GPU to the CPU. If you needed to, say, update data on the GPU side after doing some work on it on the CPU side, you then use the opposite update device. So again, now back to our file we need to work on. Basically, in Miniweather, there's a few sections that we do need the update directive in order to make sure that the model runs correctly. So this will be done at these line sections 448, 460, 828. You can also just search for to do update data. And basically, in this particular case, we're looking at, we need to be checking which data needs to be updated between the CPU and GPU for these MPI tasks we're calling. This is because MPI has to be called from within the CPU and not in the GPU. So there's some management there in terms of whenever you have an MPI enabled program running using OpenACC on the GPU. So if we go back here and scroll down over to where we need to go, not too far ahead. Let's see if I can increase the font size. Well, at least I can always zoom in. So hopefully that helps. So basically, if we open up that file here, we can search for update data. Oh. Okay, let's see. Can't see it. Update data. And there should be then these sections here that we need to then work on. So essentially we have these send buffers and receive buffers that are then being passed back and forth to MPI, where the send buffers are being processed on the GPU, and the receive buffers are also being processed on the GPU later on down here. Well, see, that's a state, that's an output. So the receive buffers are processed up here. And then the send buffers are processed later on. Nonetheless, we have to manage that movement from the receive buffers that are then on the CPU, and then make sure that then they are appropriately updated before they run on the GPU and vice versa. So in this case, we have just done some work on the GPU for the send buffers, and we now need to update them on the CPU side here. So in this case, we just want to ACC update. In this case, we're coming from the GPU, this section, and we want to update now the host or the CPU with those buffers. So basically just add this, send buffer left, send buffer right. And basically now when it reaches this directive here, it will call a movement from the GPU to the CPU and pull these buffers down so that they're ready to be sent by MPI here and this MPI send call. We also need to do the same for when we then, after receives finish here, we also need to do the same for the receive buffers where we then update it from the CPU to the GPU. So in this case, we do basically the opposite, where we now, instead of updating the host, we're now updating the device. So in this case, we need, let me grab these receive buffers here, copy the left one, and then we also need to copy the right one. So these will then run once these are encountered, where after the receives finish, it'll, on the CPU side, it'll then move the data from the CPU to the GPU, and then it'll be ready to be processed in this section of code here on the GPU side. Any questions as that's been set up? So if we go back to our exercise section, we can go through and run the new, make the new executable here. You can check what it's doing with the minfo output to make sure that those new update clauses are in fact being recognized. So there it goes through and it appears to have completed correctly, no errors, no typos I might have introduced. And you can run again that new executable to make sure that it's now correct. And hopefully this time around it should be correct. You can double check. Yes, it is. I'm very glad because I know I tend to often introduce typos. So I appreciate that in fact it's now working. So we actually see that's actually running pretty fast in terms of this test code. And again, it's with our regression test, we're making sure that it is in fact still correct. Where before it was not correct because those updates were not appropriately passing data between the CPU and GPU. So that having been done now, any questions with the data regions and update clauses as we've now implemented in our model? So I'll move on to our next section, and this is just an important one that goes towards further optimizing execution of our model on the between the CPU and the GPU. So this one covers a concept called asynchronous execution. This basically, and if you're familiar with CUDA, this is interfacing OpenACC with CUDA streams, and it allows managing directly the scheduling queues that the GPU uses to run kernels on the device in a specified sequence. So synchronous execution basically requires that anytime any action is performed and called by the CPU, it must then wait for the GPU to finish its actions, and vice versa, whereas like if there's additional work being done and called on the GPU side, it has to wait till all that's done before then the CPU finishes. And so basically they have to, all the different tasks, they run in a serialized manner to each other, even though one task may be in a parallel workload, such as with that on the GPU. So whenever we enable asynchronous execution, basically the host is then allowed to perform work while the device GPU is also performing work. So they can work at the same time because they're very distinct and separate compute units and also distinct memory spaces. So they could be doing things at the same time as each other, and thus then shortening the amount of time necessary to finish all the work that you're pumping between the different devices. One of the main things that is a benefit towards this approach is the ability to then asynchronously execute data transfers while then other computational work is being done on the GPU. Data transfers can operate at the same time, at any time any parallel work is being operated on the GPU. Additionally, for any time you launch a kernel on the GPU, there is a startup time as well as a spin down cost associated with that kernel. That kernel, those startup and spin down costs can be added as part of this asynchronous execution in a sense. Once it's scheduled to run the GPU, that startup cost is now like gone and just has to wait until there's available compute resources. So then if you can queue up many different compute kernels at once, those can then run right after each other without necessarily having to worry about and be slowed down by those startup and spin down costs. So an example way of looking at this is previously, we've been running all of our, either data movements or compute kernels in a serialized fashion where every time we call something, it has to run in a sequence such as this, where first there's a host to device movement, data movement, and then we run the compute kernel, then device to host, and the next kernel runs, and the same thing. In our cases, we were actually getting rid of these intermediary device to host movements in most kernels because we're using the data region. But nonetheless, this kernel might have to wait, and then there's like a spin down cost and the startup cost of this next kernel, and there still might be a gap between these two if you're then using a synchronous mode of execution. However, when you have a asynchronous mode of execution, you're then able to stack these up either to different queues or streams, and they can, you can have the kernel run at the same time as a device movement, or sometimes even if there's available compute resources, the kernels can overlap with each other and multiple kernels can be running at the same time. So essentially, these multiple asynchronous queues are able to be used as their available resources, but nonetheless, serialized execution of parallel kernels is not required. You are able to set these set up execution of compute loads and device movements such that they can execute at the same time. So when wanting to specify this within OpenACC, we basically have these async and wait clauses that we can add to any of our data constructs or parallel constructs in order to specify that action should be added to either an asynchronous queue, or then it should maybe wait on a particular queue to finish before continuing on in execution. So if you have async, you can also just have async without any argument, and basically it will add that execution unit to a default queue. Otherwise, you can specify any number queue, and that can help set up, say, a dependency graph between different executables or parallel kernels in terms of what dependencies might exist between them, and maybe which ones can operate simultaneously to each other. So, because an asynchronous kernel 1 can operate the same time as asynchronous kernel 2, Q2, so long as there are resources available on the GPU for both queues to run at the same time. Nonetheless, at the end of execution of any asynchronous queue, you might then need to add in a wait clause in order to make sure that everything is then synchronized before then moving on to the next step in your operations. Essentially, this, as we said, the CPU is still doing work and it's still going through your code to maybe queue up additional kernels and such. But if it queues up a kernel that, say, is running on data that's still being worked on in a previous queue, it needs to wait for that previous queue to finish before it can actually press onward. So you have to do some analysis between the different kernels to see where the dependencies lie, and thus then where a wait clause might be necessary. So if you want some more advanced discussions on these topics, feel free to review the OpenACC Best Programming Guide, and there's also a great presentation that covers some of these topics within Steve Abbott's Advanced OpenACC lecture slides. We can go back here to our basically our mini weather example. Basically, all these lines are defining our kernels that we worked on in our previous session that we're now going to make asynchronized. And all that we need to do, I don't expect, say, this time doing any analysis on dependency between different kernels. We just need to add async to all these different clauses and maybe a few wait directives between them. But nonetheless, in the way it's set up, because they all run on the default queue, as we'll be expecting, since we don't want to be adding any different queues this time, though you can play with that if you like. Since all these different kernels will be running in sequence to each other, there's no need to worry about wait between the compute kernels. We will, however, be needing to worry about wait between the update clauses we used within the MPI section of the code. So again, here's some questions here we can run. We've now edited the model a few times. This might be more for some independent work later on. But nonetheless, we can go back and check the performance of when we added the data regions, when we added the update directives, and then now when we add the async directives, and see how each of these different changes impacted performance of the model. So at this time, we can go through to the async section. We can basically, what we'll want to be doing is searching for this async me text that we have set up within the source file, and we can go to each section that's needing to have these asyncs added. So we're already in this region around the update host for the MPI section of code. But I'm going to focus on this one primarily the most, just basically because there's a particular need to be careful in terms of when we're allowing the next portion of the CPU code to be running. So when we add this async clause here, we're basically saying, as the CPU goes through, it basically, started this section, this subroutine here, it calls as MPI receives. It then, starts we'll be adding an async clause here as well. It starts an asynchronous execution and schedules a kernel to run on the GPU here. And it just submits it to the GPU, and the CPU is then allowed to continue on, counters this. This is also synchronous, schedules on the GPU. This might still be running at the same time that this is then being scheduled. So then, since it's still also asynchronous, basically the CPU will still go on and try to run these MPI sends. But if it tries to send the send buffer here before this completes, it might not have the correct send buffers as have been, both been working on this on the GPU side, as well as then actually then updated from the data movement from the GPU to CPU. So in this one case here, we will need a wait clause, and wait without any argument tells all asynchronous queues to wait. Sorry, there's my dog's squeaky toy. And essentially, now the CPU has to wait until this operation completes before it will start sending off the send buffers. So again, the same concept applies here for this maybe the receive buffers, but in this case, we actually don't need the wait clause, and that's because this one's async, this one's an async, but these both are in the default queues. So essentially, this one is already running, or is already serialized in execution in relation to this kernel or data movement kernel that's been scheduled here. So essentially, this is basically putting this into Q1. This is also in Q1. Q1 has to run in sequence to every other kernel added to that queue. So this one will only run until the previous operation in that queue has completed. So in this particular case, and again, we're using the default queue without any arguments, there's no need for that wait clause. So we can continue going through and adding these async clauses across the different other sections of the code. And basically, that's just telling the compiler to run all of these in a synchronous mode as the CPU reaches each parallel kernel to be run on the GPU. So I'm just going through, making sure I'm getting all of them. There's quite a few, so it's a little bit tedious, in terms of getting there, but it's relatively straightforward. It just takes going between each of these sections, and I made it easy with the these to-do sections, highlighting where we need to be doing this. So as you go through, you can find all of them and make sure that we have all of these set up appropriately. So we have async, async, async. Okay, I think I got all of them. I think it might be one more. I'm just double checking. Is there any questions in the meantime as you're going through this? Has anyone already added their async clauses and run the new model? Basically, once you're done, you can then run the make file here, and then run the new newly built executable, and you can see the different performance measures, performance times of the new model. So let's wait for it to go through the queue, and there it goes. So in this case, this one is about 0.48. That's actually a little bit slower than before in terms of some of these other operations you're doing. So this one, I believe this one was 0.47. And then I think this, I have to double check what that one was. That one was, okay, no, this one was 0.47. So sometimes when you do this work, there's might be some jitters between like the speed of this. I've actually gotten faster results even on this test model, but where you would really see the much faster results in terms of this particular new execution. So you see with just data clauses without the, we got 1.38 here. We're making incremental improvements, but really where this will likely be more apparent is if we're running on a much larger model. So in this case, we're using only the test size of the model, which is about 100 by 50 domain size. And so if we increase the domain size, there'd be much greater utilization of the GPU. And thus then we'd see a more accurate representation of how these clauses are impacting and perhaps improving and sometimes decreasing in performance. So there's a question in the chat: doesn't the host update? Does the update host need to wait until the do loops on the device just above to be done? Around line 430. So let's see, let's go to 430. Just to talk about like before the I receives here. And in this case, these receive buffers are basically just we're receiving them from other tasks. And 454. This is why we added here this wait clause here. We have this after we've now done this processing on the send buffs. We'll want to update the host, send the data from the GPU to the host, and then you have to wait before it's allowed to then send these buffers to the other MPI tasks. Basically, from the other perspective, hopefully you're somewhat familiar with MPI. This is the task that's now waiting for the send task from the other processes to complete. And so once this one is done, we now then have received these receive buffers. We then go on here and move the receive buffers from the CPU to the device and then run them here. And we can keep going on our merry way through the rest of the program as it runs. So essentially, after having done all that, encourage you maybe to play around with different implementations and see how that impacts performance, maybe running them on the V100 when we're outside of this workshop. But with the remaining 10 minutes we have I'll talk about some more advanced concepts as we have time, but feel free to reference these later slides for your own review and discussion about some other clauses and directives we can use within OpenACC. Again, you can reference specific lecture slides that cover some of these more thoroughly. These are linked here appropriately. One of the main points I want to make here before going on, and we'll touch on later when we talk about profilers, is that there's a particular cycle in terms of how we're running and modifying code and making sure that we're actually getting performance gains as we're making all these changes. So the best course of action after you learn how to use OpenACC and actually make a model run on a GPU is you want to then analyze and profile that model using something such as Nsight Systems or Nsight Compute. We've been so far using the basic profiler built into the compiler through that NV and that timing environment variable that we tack on to each job. But nonetheless, you analyze the performance of your model. After that, you parallelize it, maybe actually check different sections. Maybe there are hotspots and taking a long time, maybe on the CPU side, maybe there's some additional sections you can parallelize. And then after, maybe if you've already parallelized sections, you can use that profile to see which ones are running slowly and then further optimize them, such as what we just did. And basically this cycle just goes round and round as many times as you like for however as fast as you want to get a model. And ideally, OpenACC will enable much of the optimizations that you should be able to explore towards getting the best performance you can with whatever program or scientific research you might be doing with this programming model. Nonetheless, as I mentioned before, if you want the best possible execution possible, you would maybe really would want to be looking into some of the CUDA accelerated libraries such as QFFT or QBLAS, or maybe even then write your own CUDA kernels. And these can be tied into OpenACC wherever they might be most needed. So some of the things I focus on here, at least just in structure of maybe your code, is this routine function. So say you're within a GPU kernel, a parallel construct, and you're trying to call an external routine, but that routine, at least on the CPU side, is really only visible as a CPU routine. So then if you're within the GPU and it tries to call that function, it will not know what to do with it. So in this case, you might need to then add the ACC routine clause in order to tell the GPU that this is a GPU routine and it should then run on the GPU. One additional factor you need to add when you are specifying that is the what type of parallelism it will run as. If we talked previously about vector, worker, and gang parallelism, it also might need to be run sequentially. You basically need to specify that level of parallelism for that routine. So if in that routine you do have like another a GPU parallel region, such as ACC loop vector parallel construct, then you might say specify that that routine is a vector routine. If it's just a simple routine, there's no like parallelism inherent in it, you then just want a sequential routine. So in Miniweather, there is one routine that you can set as a GPU routine, and that will then, but in the current implementation, it is actually inlined in the model. This inlining actually tends to perform better than letting the compiler navigate how to do this jumping between the CPU and GPU routines. But nonetheless, if you're wanting to have a readable code or something that's accessible to other programmers, you might be reliant on, say, using this ACC routine directive instead. Basically, you can run through that exercise, try it out, see how it impacts performance. Usually it tends to slow it down for most compilers. Some compilers are getting better at it and it might not impact performance much, but nonetheless, this is one option towards doing that work. You might also say, look into like other algorithms that Miniweather is running and think about if there's like, and maybe even try out different subroutines you might create that then you can run as a GPUized routine using that ACC routine directive. So again, you can run through those examples. Other things we want to talk about in this more advanced section in the next 3 minutes before we go into questions. Essentially, as I mentioned, you can run you can run like OpenACC in a multi GPU programming model aware setting using a CUDA aware MPI feature. And basically that is often enabled through some of the specific runtime library routines that are available, made available using the OpenACC module in Fortran or the OpenACC.h header in CC++. These basically provide many different specific routines you can call from the CPU side to say get the number of devices that are connected to the host. Say if you have a multi-GPU node that we like we have on Clasper, where we have some 4 and 8 GPU nodes. You can also then set a specific device to run on. So by default, you're always running on the 0th device, the 0th GPU. But if you have multiple GPUs, you can then tell, say, across different MPI tasks that you want to run on GPU 0, or you want to run on GPU 1 or GPU 8, however many you have attached. Actually, it would be GPU 7 in that case. But nonetheless, these type of functions exist for enabling that type of feature. There are additional routines you can explore. Feel free to explore the specification from OpenACC for learning more about that. But nonetheless, that feature exists and is a way in which to interface outside of OpenACC with the main CPU execution of your program. One of the next things we'll talk about is the basically linking up OpenACC and enabling interoperability with, say, CUDA libraries or, say, CUDA kernels you develop manually. This is enabled through two types of clauses and directives. One is device pointers and the other is host data use device. Basically, that pulls the device pointers clause. You can then specify within a compute region and tells that compute region to use a variable that's already been allocated on the GPU and does not need to, say, move data at all between the device and memory. Basically, say if you have already initialized a variable with CUDA malloc and it's not actually in CPU space, then you would need to use device pointers to then tell that the compute kernel or a CUDA library to use that particular variable as it's been initialized on the GPU. On the other side of things, if you have basically if you have a section of code that already has a variable on device the same, you can use a host data use device setting and region of code to allow calling a CUDA kernel from outside a parallel region. So these are kinds of options you can use for exploring this. And one example that I'll focus on briefly before we go into questions is this Q-tensor example. So I encourage you to look through that. You can see here, maybe we're using OpenACC, so opening up that library and the routines we want to access to. We also have the Q-tensor library we're loading in as a module. And essentially, we basically can copy in these variables in our compute region. This one basically is just a kind of a directive flag that's saying, as long as we're in OpenACC mode, we can then run this on the CPU. So here we're getting a stream value for the Q-tensor library, and from there we can then tell the GPU section here, the parallelized section here, to use the device memory addresses after they've been copied into that section. And so here, this mat-mul, this intrinsic here within Fortran, which is now remapped to Q-tensor when we load the Q-tensor library, this will now use the GPU device memory addresses as opposed to the CPU ones and not throw an error when we're in that parallel region or data region. So this is just one example use case for that particular application. But there are other libraries you can explore in terms of how they're implemented by following this link and reviewing the many examples included in the HPC SDK app documentation. So the next few slides I have just type of more advanced optimizations using cache and tile. You're more than welcome to review them on your own time. I would encourage them also manually tuning many weather and exploring how they impact performance utilizing some of those additional more advanced optimizations. But given we're about at time, here's just the last amount of suggested resources, and I'll leave you to any additional questions we may have from the group. So thank you. If you have any questions, feel free to either add them in the chat or raise your hand and unmute yourself and we can discuss live. So I'm going to go ahead.